This is Chapter 8, Section 3. We've already done the series and parallel circuits, and now this section deals with, okay, what if we make a complex circuit? How do you deal if you have series and parallel together? And the first thing is a reminder. This was basically that last slide that we looked at, and I said make sure that you know this. It was for series and parallel, and it showed current, potential difference, but it also showed equivalent resistance. And the difference between series and parallel, is it the same for the entire circuit, or is it an additive process? As I'm making up y'all's test, it is extremely important that you keep all of that stuff straight, because if you accidentally get, say you're additive versus it's the same, and you get it mixed up between the two, you will miss, if you have it wrong in your head to start with, you will miss 90% of what's on the test. Okay? So very important that you keep straight. Is it additive, or is it the same throughout, depending on if it is series or parallel. So, keeping that in mind, we said current for series is the same as the total. So if you have multiple resistors, the current's the same over every resistor, but for parallel, it's additive. For potential difference, summative for series, but it's the same for parallel. What was it for equivalent resistance for series? Do you remember? So the
series, it was the same for series. It was additive for series.
So for equivalent resistance for series, additive. What was it for parallel?
The opposite.
What does that mean?
It's the same as the total.
It was the reciprocal.
Oh, yeah.
So 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2, and you just keep on going. So that was the reciprocal. So that was the one case where it wasn't just flipped like the other two are. It is an additive process, but one of them is the additive of its reciprocals. Definitely keep all of that straight. Very important.
What was that for, reciprocal?
Yes. That was for the parallel. It's 1 over the equivalent resistance equals 1 over each individual resistor, and you add it up. And you should have that in your notes. Like I said, I'm pretty sure I had y'all write that down at the end of section 2.
Most real circuits contain both series and parallel arrangements. For example, the appliances in a house are connected in parallel, but the circuit breaker that protects them is in series with the parallel combination of appliances. The circuit must be separated into parallel and series elements in order to determine the equivalent resistance. The circuit must be separated into parallel and series elements in order to determine the equivalent resistance. First, the resistance network can be shown in a simplified drawing, allowing a clearer picture of which resistors are in parallel and which are in series. The diagram shows the parallel combination of resistors that must be simplified first. The equivalent resistance for the parallel part of the circuit combines in series with the remaining resistor. The circuit breaker's resistance is so low that it doesn't appear in the final result. Without doing the analysis, however, we could not have been sure that was the case.
Okay, so that's what you're going to learn how to do today, is do your own calculations based on you having different resistors or different loads that are going to be in series and parallel. So this is the sample problem that we've got here, and I think that I'll probably end up drawing this on the board, and then we'll work through it the way they want to, or we can just work through what they've got. But if you redraw this, how would you want to redraw it so that you can keep everything together, like what's in series versus what's in parallel?
Everything in ohms together, and then the 1 volts.
Okay,
separated.
so that's your battery supply. They're going to show you how they're just going to put it all out in a straight line, because which ones appeared to be in parallel?
The 6, 2, and 4.
Okay.
Squared.
So the 6, 2 up at top is really in series with each other, but as a combination, they're in parallel with the 4. But then you take that whole thing, and it's in series with the 3, the 6, and the 1. So that's what this is going to go through.
3, 6, and 1 in series with each other?
Yes.
Okay.
Yep. And they're going to show you how to break this down and look at each individual part. So the math that we're going to do is the math that we did in section 2. It's trying to get to the math part. So it's talking about how to approach it. And we've already done sample problem A and B. And then they're going to show you this redrawn. What have they taken out?
The volts.
Okay, so they're taking out the battery. They call it in the tip the EMF source, and you work with just your resistances. The original question on this was determine the equivalent resistance of the entire circuit. And like we stated on that first slide where you had it drawn in there, it's additive if you're talking about series, but it's additive of your reciprocals if you're talking about parallel. So you can't do it all together. You got to kind of break it up into chunks. If you were doing this yourself, where would you want to start? With the parallel ones? What do y'all think? No? What would you want to do?
I would do it like this.
Which way?
I would do it like that.
No, I'm saying when you go to do your calculations, where would you want to start?
Would you get the 6 and the 2 that are in a series and add them together, and then add that to the 4?
Yep, so you'll have to take care of the 2 and 6 first. And then you will take care of the entire parallel section, and then you could go back and do everything in series. And that's how they're going to break it apart here. So we've got our different components. And notice that's what they did. They went ahead and combined what they're calling in part A, the 3 and the 6. How did they do that? How are the 3 and the 6 combined? Series or parallel?
Series.
In series, and that's what they've got in blue. And they went ahead and added it. Could you have done that at the very end?
Yes.
You could have. And then they take the 6 and the 2, which are also in series, and they've added those to get an 8. And I don't see what the last part is. But there it is for Group A, there it is for Group B. Both of those are additive, so they've just handled some of the things that are in series. So some easy math there. Now, moving on to what's in parallel. So you've got Group C right here. You have the 8 ohms, and then you've got the 4 ohms. Do you see how they got 2.7 ohms for the 2 sets in parallel? I'll give you a second to look at the math that is associated with it.
3 and 6.
Mm-hmm.
In this chart earlier, it says if you're finding the total for series, you're saying it's total,
Uh-huh.
but we added them. So I'm just like confused. Like, is it because you added it? It's the same as the total. Like, do you see?
No. What was the very first part?
Okay, so we added like the 3 and the 6 and the
Because
6
they,
and the 2.
the 3 and the 6 at the very beginning of this. Let me get out of here.
That's the resistance.
The 3 and the 6, notice both of those are in series with each other. So if you're talking about series resistors, it is straight additive. We added it up. The 6 and the 2 are both in series with each other, so we add it.
Okay.
But once we do that and we get this part right here, the 8 and the 4, those two are in parallel with each other. So now we're going to have to go back and do all of our reciprocal additions for the parallel part. And that's what they're doing on the next slide is the reciprocal additions of those two. So they've taken it and they've moved their picture down just a little bit so that you can see everything and showing you adding those two.
So how'd you get from 0.37 to the other one again, to the answer of 2.7?
Let's go look at the math. Because this is really what you've got once you do that. You've got Yeah. Yep. You've got 1 over equivalent equals, what did they have? The number they had was no. What was it? I just don't see it written on mine.
2.7.
No, before the 2.7.
2.5.
So they had 0.37 ohms right here. You have to get the equivalent resistance out of the denominator. So to do that, if you bring this over, you're going to multiply, but then you have to take the 0.37 back over and divide. So you end up with 1 over 0.37 equals your equivalent resistance. And then you solve. So 1 divided by 0.37 gives you, is it 2.7?
2.7.
2.7.
Is it 1 over 0.37?
Yes.
Because, like, on our PowerPoint, it shows the 3.7 on the top.
Well, it is. But if you're looking at this part right here,
You have to take the reciprocal.
yeah, because it's 1 over
Yeah.
equivalent is equal to 0.37. Now that you've got that, you can see that everything that you're working with is now in what type of setup? The 9, the 2.7, and the 1.
Series.
It's all in series. So you can take this, and then you can go and do an additive process of those three. The 9, the 2.7, and the 1.
And that gives you equivalent.
That is your equivalent resistance for the entire circuit.
Okay.
Now, keep a hold of those numbers because the next sample problem they do is going to take this same circuit, but it's going to ask you different questions besides total equivalent resistance for the entire thing. So our problem now is it's going to want to know current and potential difference. So current and potential difference across the 2 ohm resistor only. So current and potential difference across the 2 ohm resistor only. Based on the chart that we looked at the very beginning and at the end of section 2, what are some things that you can say about current of the 2 ohm resistor?
It's same throughout the whole thing if it's in series.
If it's in series, then it's going to be the same throughout. So at some point, whatever we get, expect your current to be the same throughout since it's really initially in a series setup. But we have to get to that point. So let's focus on current first. What do you want to do?
First, determine the total current.
What is the formula for current?
I equals
Delta V over REQ.
Okay.
I'm
So
just guessing.
I is delta V over equivalent resistance. Delta V is what?
volts. So it's your 9.
So that's our 9 volts. Equivalent resistance, we calculated it earlier, is being what?
You use the equivalent resistance for the 6 and the 2 or for the whole thing?
Which part do you think?
The 6 and the 2.
Okay.
Right on that.
Let's see here. I got to go look at what numbers we actually had.
See what PowerPoint says.
Well, we calculated REQ for the whole thing, right? Like
We did.
12.7.
We did.
Yeah, it says it's 12.7 on PowerPoint.
Okay. I don't have my numbers on here. I got to go find it in the book because I just don't remember what the numbers were. So you got 12.7, and then what is your current?
0.71
So 0.71 amps. And then this one right here, your delta V, it's going to be broken down for a series circuit, and then you back calculate it, but for current, what's your answer?
For which one?
For current, Can we just leave it like that, or do we need to break it down?
We need to break it down.
Well, current is 0.71 amps across everything, but that 2 ohm resistor, isn't it also part of a parallel circuit too?
Mm-hmm.
So could we just stop right there at the 0.71, or is there going to need to be a further calculation?
There needs to be a further calculation, but I don't know.
Okay, that's what it's going to take us through. I just want you to recognize if you need to go further or not. What if it would have said, like across the 6 ohm or the 3 ohm? Would you have done anything further?
No.
With
Okay.
those 2 6 ohms, are you talking about the one
Oh, yeah, well, the one that is
with the 3?
right over here.
Yeah, gotcha.
Okay? You know, ask yourself, do I need to go further?
No.
No. But the other one, because it's really part of a parallel circuit too, you're going to have to take it further. So write down the current right there as being 0.71. I'm going to write it up here just because I don't have it on my stuff. So I'm going to put that as total, 0.71 amps. So if you're looking in your PowerPoint, we've already talked about this part, and we've talked about the next part too. And we've done our calculation with that. So we got the 0.71 amps. Now it says, determine a path from the equivalent resistance found in step 1 to the 2 ohm resistor. And you can see where we've already done A, B, C. They show you right there where we did part D, which we've already completed it too. I'm going to give you a second to read that, and then we'll go through it.
Got it.
It's this. It just does whatever it wants to when it wants to.
I don't remember being this bad last year.
Oh, it was. It was worse at times. Okay, so moving on with this. They're regrouping, evaluating, and calculating, but again, where you see the 2.7 ohms, you've got that there. We've got delta V equals I times R. Does that equation look familiar? Delta V equals I times R? What is that?
That's I equals delta V over R.
Yep, so it's just the same equation. They've moved everything around to where you're looking for delta V first, so potential difference. So we've got current for the entire circuit. We have equivalent resistance for the entire circuit, and they're wanting to know potential difference. Multiply those two, and this again is for the entire circuit, and you get 1.9 volts.
Wait, I thought you said we had to do something else with our current.
No, that's potential difference.
Oh, okay.
That's potential difference.
I thought that the 12.7 was our.
It is. But this right here is for, it asks for just the 2 ohm circuit. So this 2.7 was in that cluster that included the 2 ohm circuit, or the 2 ohm resistor. Do you remember this one right here? That had,
Oh, yeah.
what were the numbers?
9.
It had the 6 and 2 on top and then the 4 on bottom.
So even though we just
That's what was in parallel.
So we just used that one, but we used the whole current.
Yes, because for potential difference, if you're in parallel, it's the same as the total.
Okay.
That's where it's the same as the total.
Okay. Hold on. Right. So the 8 and 4 were the ones in parallel, right?
Yes, and if you back
And
up,
then
the 8 was the 6 and 2 that were in series that were part
Right,
of the parallel.
Right. And then you did the reciprocal thing and found 2.7.
Well, we did that earlier. That
Yeah,
2.7 is from
exactly.
earlier.
But that's
Yep.
where that number came from.
Yep.
Okay.
Any other questions on this one? So that's potential difference. And now we're going to go back and look at current. And again, they're regrouping this stuff too for current. So you've got our potential difference of 1.9 volts, and that's what you've got there in that parallel mini circuit that we've got going on. And then you've got a resistance of 8 ohms. Where did the 8 ohms come from?
It
The
was
6
part
and
of
the
the
2.
6. Yeah, the 6.
That was the 6 and the 2 that were in series together, because we're trying to back it up to just the 2 ohm. And then you've got current is 0.24 amps. Why did they use the 8 there?
Simpler. Or
Because you're
To use the whole series.
using you're using what's in series. Because it was the
Because
6 and the 2.
6 and the 2 was
And you're
in
looking
parallel.
for the 2. So you're working
Or was in
backwards.
series.
Okay. And if I go back to current in series, it's the same as the total. So earlier we did potential difference in parallel was the same. Now we're going back to current in series is the same. That's why you can use the total value there instead of just individual values.
So the 0.24 amps is for the 8, right?
That is the current that is going to be for that small little cluster of the 6 and the 2. The 6 and the 2. We still have to get that value right there for current is going to be the actual value for current that we're looking for. Because if they would have said, what is the current for that top 6 ohm resistor that was within that same little cluster for the series, that would also be the answer for current, because current in series is the same.
Right. Oh, yeah, right.
But we're still not finished.
How?
Because the current that we found earlier, what was it for?
Total.
The current that we found earlier was for everything in the parallel path. We still have to go find the potential difference for just the 2 ohm resistor. So what values would we use now for a potential difference of just the 2 ohm resistor?
It's the 0.24 amps.
Yep.
And then
And then the 2 ohm resistor
Yeah.
itself. So it takes you another step to get to that point. So there that is calculated for your potential difference. I noticed as I was going through working everything out on y'all's test, and I will go back and show you the thing that I was looking at to make sure that you definitely don't want to get messed up in any way. But anyways, that is going to be your final answer there, the 0.48. But let me show you what I was talking about. Yeah. This was at the end of section 2, and before I started working on y'all's test, I made sure I had that written down, series, parallel, what's going on with current, what's going on with potential difference, what's going on with resistance, depending on if you're in series or parallel. Because like I said, if you get these backwards, let's just say you totally got each of them reversed. You remembered everything but had them reversed, you'll miss at least 90% of what's on the test. Okay? If you just get, say, one piece mixed up, it just depends on how complex the question is. If it's something real easy like just series or just parallel, you might have a decent chance of getting it worked out. But once you get into the complex ones, you could see how many steps we went through. We kept switching between what are the rules for series versus what are the rules for parallel. And if you don't have it all straight, it could be very confusing.